Good afternoon. Welcome to the CERIAS Security Seminar. It's my great pleasure to introduce today's speaker, Dr. Kui Ren. Dr. Ren is Associate Professor of Computer Science and Engineering at the SUNY at Buffalo, and he's also the director of the UBSec lab there. His research spans security and networking, including cloud and outsourcing security, wireless and wearable system security, and human-centered computing. Professor Ren is the recipient of NSA Career Award in 2011 and a number of other awards. Today he'll talk about breaking mobile social network.
Thanks for the introduction. Today I'm really glad to be here to share one of our recent studies on the mobile social network security. The title of this talk is Breaking Mobile Social Networks for Automated User Location Tracking. And here's the outline of the talk. We're going to start by introducing the current location information management practices in today's mobile social networks. And then we will move on to the attacks that we identify, which enable us to track the user locations. And then we will move on to how we conducted the attack in the real-world setting and report the experiment result. And then if we have time, we will talk a little bit about the defense mechanisms, and then the talk is concluded. So mobile social networks, so they are so popular nowadays with the ubiquity of the smartphones, right? And billions of users are actively using them for social interactions on a daily basis. And very successful examples include Facebook and WeChat, Google+, WhatsApp, so on and so forth. And location-based information are really important in these mobile social networks because they are key to the user interaction experiences in many networks today. And this location information enable and facilitate a lot of location-based social interactions. And here are a few examples that we look at it. So, well, the location information are being used in the social networks. For example, check-in services. So allow users to check in to report their locations. Examples include Facebook, Weibo, Foursquare, etc. And geotagging, right? And when you post a message, there's a location information is being attached to that particular message. And the examples also, they are also very popular in different mobile social networks. And there are also location-dependent comments. For example, in the case of Yelp, when you visit a particular restaurant and you leave your comments, that basically shows that you have been to that exact place. And also, most popularly, proximity-based friend discovery or social discovery, and that is the focus of this research. And before we conduct the research, and the first question we ask ourselves is that how do the existing location-based mobile social networks acquire users' location, and how do they get the user location? So basically, the approach is as expected by everybody else, right? Mobile users voluntarily report their location via the client-side app to the LBN service providers. And there are various types of location information being collected depending on the availability at the time being, right? It includes Wi-Fi signal, if they are available, or GPS, if you are in the outdoor apartment and you have a GPS chip, and all cellular tower ID, right? And this different location information, they have different accuracies. The Wi-Fi, these are the numbers we cited from the references. The Wi-Fi maybe gives you a 80 meters range of accuracy. And GPS gives you around 10 meters of range. And while the cellular tower ID gives you a very coarse-grained information around 600 meters. And they are being collected in a periodical, on moment, or combined fashion, right? And there are different ways to obtain from those information sources. For example, in the studies that we look at the different service providers, the WeChat and SkyOut basically select the available one with the highest precision, right, by interacting with the Android framework. So, for example, GPS, Wi-Fi, or CID depend on at that time what kind of location information is available. But the apps like Momo does not allow you to directly request from the system, but it rely on certain SDK. In Momo's particular case, it rely on Baidu's location SDK to fuse the input from different location sources. So then we want to know how accurate the displayed user location information in the apps, right? Suppose the app says the location is, the one user's location is at a certain place, but how accurate it is? If it's already, adding a lot of noises, maybe the users are already better off because their location, their accurate location information is not being displayed, okay, in the system. So we want to study that. We feel that, okay, this location accuracy displayed in the client app, it can be reflected by the distance between the user's real physical location and the displayed location you obtain that indicated by the app, right? So we found that location accuracy varies across different LBSNs, and they are dependent on two things, right? First of all, the available location information sources at that, for example, at that moment, you are indoor and you only have Wi-Fi connection, probably, it is less accurate when you are outdoor and you have a GPS signal. It also depends heavily on the internal processing strategy, okay? As we will show through our experiment, how different apps treat the location information in a different way. But the overall observation is that the LBSN location readings are still quite accurate. And here's the accuracy testing we did towards several popular LBSNs. And the way we do it is that we want to study the difference between the real distance of the two devices, okay, versus to the distance readings on the popular different apps. Okay, so basically what we did that we first run two instances of the same LBSN service into different virtual machines. And then we fix one reference point in one instance and move another test point along a straight line so that we know how we move the distance so that we have the ground truth. And then we refresh the app and refresh the status, and we try to identify the readings. We try to read the readings from the app, and we compare the two, and we try to find the difference. And obviously, in the ideal case, they should be the same. However, in reality, they are not, and they vary across different apps. So here's the result we found. Okay, so these three figures shows the experimental result we did for Momo, Scout, and WeChat. And here's the result. First, for Momo's case, the distance readings are always rounded at 5 meters. So that's basically to say that if it shows 5 meters away from each other, the real distance is anywhere between 0 and 5. If it shows 10, it's anywhere between 6 and 10. That is the Momo's situation. And then you look at the Scout. So Scout basically rounds up the distance reading every 1 mile. Okay, so that basically says that if it says you guys are, two devices are 2 miles away from each other, the real distance is anywhere between more than 1 to 2 miles. Okay, and also the Scout impose a minimal sort of distance accuracy. That any two devices whose distance is smaller than 0.5 miles, it just stops there. Okay, so if the real distance between two devices are between 0 and 0.5, it always indicates as 0.5. Okay, so that's the case for Scout. So so basically you look at the figure if you can this staircase shape. And in the WeChat case, we found the two characteristics. First of all, the location precision, the distance precision, rounded at every 100 meters. Okay, so if following the same logic, right? So if the two devices indicated to be 100 meters away from each other, the real distance is anywhere between 0 and 100 meters. And also, yes?
So do you think why Scout is doing that? Are they doing it for privacy protection? So they round it off, or they actually don't get the accurate data?
Yes, we will talk more along that direction later. So, but WeChat also imposes another constraint. Basically, in the metropolitan area, it does not indicate any user that are further away than 1 kilometers. Okay, in the rural area, that number increases to like 2 or 3 kilometers. Okay, depending on the population density. So that's another that's the practice that we find from WeChat. So next, we want to find out how are the location information being shared among LBSN users. Okay, we did a lot. We did a long list of survey, and we basically characterize them into 3 broad categories. The first, we call it open direct access to any registered users of the app. Okay, so sharing exact location information among any users of the same app. Okay, so basically there's no location privacy at all as long as you are willing to using that app. Okay, the other one is called authorized direct access. So basically you only share, you still share exact location information of the users, but only among authorized users. Okay, not any other user of the app, but they are friends. Okay, you only share the exact location information among friends. And then we call it another type is indirect access with constraint. So basically, in many cases, the exact location of the users are never disclosed, are never displayed, but they show it through an obfuscated way. And the common practice is to show the relative distance between the 2 devices instead of the exact location of a particular device. And on top of that, it's subject to various additional constraints. And this is a simplified survey result, right? And in the paper, we have a more exhaustive list. So you can see in the iAround app, which has, at the time of being surveyed, they have 10 million of users. It has open direct access to the exact location information. Okay. In the Google Plus and Facebook, they have authorized direct access, sharing exact location among users. But in the case of WeChat Scout and more, they never share the exact user location. So they have a lot of users. So here's a closer look on the constrained indirect access in LBSNs. So first of all, showing the relative distance between the users. Okay, Momo displays relative distance with a precision of 5 meters, as we just pointed out through the experiment, right? And users see their distance to other users instead of exact location. And that's sort of the way, you enable location-based services, but you somehow also protect users' privacy as they expect, as they want, okay? And the service provider want. And on top of that, not only we just show the relative distance, but we also want to impose more strict limits so that we can, while preserve the utility, right? Meaning enable the location-based services. Still, we want a better protection over users' location privacy. So Scout basically imposes an additional constraint saying that when 2 users are smaller than 0.5 miles away from each other, we just stop there. Okay, we never indicate any distance smaller than 0.5 miles. Okay. So, and every time the precision is at 1 mile. Okay, that's one of the additional constraints that Scout considers. And the other one is imposing a maximum distance constraint. In the WeChat case, any user that is 1 kilometer away from you, so it is not indicated in the app. Okay, of course, the precision in the WeChat case is 100 meters. So that sort of survey and analysis bring us the following observation, right? So the current LBSNs, they rely on indirect and constrained location sharing. Okay, so that exact user location information never shared among users, so that they want to strike a utility and privacy trade-off. Okay, and these are the current industry best practices. Okay, so it's deemed by most popular LBSNs as a desirable middle ground for protecting both location privacy while enabling effective location-based services. Okay, that's our observation. So now we want to move on to the attacking part. So we basically said that kind of protection is not good enough at all, and we can easily attack it. So here is the attack goal and the assumptions. So we assume only a very weak outside adversary. Okay, so having exactly the same privilege as ordinary users. And we do not hack into the LBSN service provider, their servers, we don't. We just treat the service as a black box. Okay, so we only exploit the publicly available information. Okay, and yet, such an adversary is still able to achieve both localizing an arbitrary user with very high accuracy and performing long-term tracking and eventually try to reveal the user's identity information with high probability. And that's the goal and the assumption. And then we start to describe the attacks. So first, the attack targeting. So we have like two different types of targeting, right? So first is selective targeting. So you know a particular user ID and you want to track him or her. Okay, the attacker is able to locate a user if he knows the user's ID for that particular app, right? The attacker does not have to be the victim's friend. Okay, for example, in Momo, distance readings can be retrieved when the attacker searches the victim by user ID. And in Scout, the attacker sends a regular message to the victim, okay, not necessarily his friend. The relative distance will be displayed for the following queries. Okay. And there are also random targeting, right? So you just set your GPS location in an arbitrary venue, and you search people nearby, and you select whatever user ID shows up. Okay, so within a certain range. That's the way you do the targeting. Okay, then the attack overview. So we focus on finding client-side app located on the user's mobile device. Okay, and we develop an automated system which can be easily scaled up to handle multiple concurrent targets. Right? And basically, the way we do it, that we exploit the localization service protocols to fake the locations of the anchor points that controlled by the adversary. Okay, and modify the Android framework to dump the location readings to and inside the LBSN. And this picture on the right basically shows that the attack logic, and we run the mobile app, mobile social network service apps inside the Android virtual machine. Okay, this attack logic basically calculate the fake locations and update it and feed that information to the app, and in a multiple round fashion, so that eventually it will converge. And when it converges, output the estimated attack location. And the attack logic is simple and does not have to be fancy. So the key idea, trilateration, right? For example, Momo choose relative distance between two users, right? So suppose this star is what we want to localize the user, okay, in a particular location. So obviously, if I have three anchor points, all of them showing this user is within their range, the relative distance, saying that this is 2 miles, this is 3 miles, this is 5 miles, then this trilateration will give you a good idea about the exact location of the user. And of course, it is not accurate enough when you just do a one round thing. So you do it in a multiple round fashion and you try to converge. Eventually, you will have a very good accurate estimation about users' location. And that's the starting point. And then to further deal with that, the minimum accuracy constraint, Scout basically says that any distance smaller than 0.5 miles, we are not going to indicate that. So in that case, we will basically choose the petition. But the idea is still straightforward, right? If the user seeing another user is the victim, is within smaller than 0.5, saw that user with smaller than 0.5 miles, he will know the victim is anywhere inside this blue circle, right? And by update his own location and check if he sees check if the location reading is how the location reading is being changed. He will know that which area that victim is. So you keep changing your own location, and eventually you will know. I'm sorry, it's just a little bit delay. Yeah, eventually you will be further narrow down the location of the victim. So basically, you use the trilateration to get a rough estimation of your victim, and then use space partition to further narrow down your target. And of course, to deal with the VChat additional constraint basically says that any user further than 1 kilometer away from you is not showing in your friend list. In that case, you just to have a good estimation about where the victim is and try to scan the whole area. Okay, so that's also straightforward. Of course, then if you have a good estimation about where the victim is, it will simplify your effort, right? But if you are going to search on a global base, the converge time will be much longer. Okay. Of course, then last December I visited one of the research institutes in China, and they followed up our work. Basically, they said that they deploy a large number of virtual machine instances. Each instance has a different location, form up like a grid system covering, let's say, the whole Chinese area, right? So that it gives a good. So that when you try to locate a particular user ID, it takes much less time because you already have those virtual machine, those instances being running. Okay. Okay, now it's about system implementation. Right. So the attacking logic runs inside the host machine. Okay, and we also run the mobile social network app inside the Android virtual machine, and we also write the location faker app running inside the Android virtual machine. So the attack logic basically carries out the localization calculations, okay, and communicate with the location faker app in the virtual machine to set fake locations, and also trigger location update operations, right? Because you have to simulate the user's input, right? Either the screen dragging or scrolling down and all that operations, and also reading the information from the Android ADB logs, try to extract the location information in a digital format. So the location faker app in virtual machine set fake locations by first use Android's mock location provider, because Android, for the debugging purpose, Android system allows it, right? Act as a location server that answers the location request from the social network app. And there are two different ways when the LBSN app requests the information, as we introduced earlier. So first of all, the first type is that they basically try to get the location from Android system, right? So in that case, we implement this test location provider and feed the app with the fake location. Or in the case of Momo, they use Baidu SDK. So they try to use that API to query the location information, ask Baidu, saying that, hey, where is my location, right? In that case, we implement this kernel firewall called IP table, right? That's already there. We just use it to intercept the network traffic and redirect that back by feeding our fake location to the client app. So here are more details, right? So Android system allows setting mock location via the test location provider for the debugging purpose. And our location faker implements a test location provider. So location faker can accept the request from the attacking logic unit and update the locations. So whenever you want to, okay, so the computer acts a little bit delayed than expected. So you basically feed the fake location to that. So in the Momo's case, because they use the location API to query for the location, so basically we use the firewall to intercept the traffic and redirect that and feed the app with the fake location. Okay. So reading locations from the apps, because when you implement system, so you will see that all the text-related information is displayed in a widget called text view provided by the Android framework. And the widget has an interface, text view.setText, which is called by the apps to show the text. And so from the screen, you try to extract that smaller than 0.5 mile information digitally. So we modify the code and log them, basically, to the ADB log buffer. So in that case, we get all the digital information of the location information stored. And the location update operation in the app consists of multiple tapping, dragging due to the screen size of the mobile device. And we have to be able to simulate this input to refresh the location of the app. Okay, because we want the automated approach. We run the app inside the virtual machine. Right? And we also mimic the screen scrolling with multiple drags to deal with the long user list to read back all the distance readings. And that is also important. And that's basically the attack overview and the system implementation aspect about the attack. So here's, we move on to the attack experiment. So basically, we performed a 3-week-long evaluation with certain volunteers from China, Japan, and the US. We focused on first the tracking accuracy, right? We did both synchronous tracking and asynchronous tracking. And we also want to know the localization efficiency, right? And the effectiveness of the long-term tracking. We also did a little bit of that. The first part is synchronous tracking. Basically says that we want to roll out the inference from the user's mobility. We just want to know what is the best result we can get. So because these volunteers we recruit, they basically we write a ground truth recording app inside their phone, right? So they record their exact location all the time, right? And then we run our attack and we try to localize them and we compare the two because you have to have the ground truth to compare with. And when you report your location, you stop there and wait until the attack completes so that we know that this is the best. And then later on, we do not prevent the user from moving. Okay. So the user refresh the location readings on the app and report their location to the server, our attack server, right? And upon receiving a report, the server launches the attack immediately. And when you get the result, you compare, and this figure basically shows in the time domain this action, how these actions have in a sequential manner. And the accuracy is measured as the distance between the inferred location and the user's real location. Okay. And we show this result. We find that it's fairly accurately. These pictures may not be that clear, but just from the result, in the Momo's case, 60% of users can be found with an accuracy of 0 to 20 meters. Okay, so basically, if we say this user is here, it is within like 20 meters range, 60% of the chances. Okay, and this is basically what we did. And some of the result when we did the experiment, and you see some tail statistics, is because in the reality, when user, we found that it may be because of depend on the availability of the location information. Sometimes you rely on Wi-Fi, sometimes you rely on GPS, sometimes you rely on CRID. And these students, sometimes they use subway, they use different transportation approaches. So an asynchronous tracking basically is that we want to know in reality when we do not enforce any mobility constraint on the user and how well we can do, right? How well we can perform. So we basically, in that case, we just again use that ground truth recording app located on the user's phone to periodically report their real location. Okay, and then we launch the attack also periodically at a lower frequency. And whenever we get the result, we compare in the time domain which are the close to location information. We compare the distance, and that way users move all the time. Okay, we do not interfere with their mobility pattern. So the volunteers carry an app that automatically report location periodically. Attacks are scheduled at a lower frequency, and again we measure the distance between the inferred location and the real location. And we found that the result, of course, the performance degraded, but disgracefully. For the Momo's case, previously, as I said, 6% of chances, but now it's 40% of chances. And that's depend on the mobility pattern that the volunteers have. Okay, some of them, they are working, so they do not change, the accuracy is high. But if you take the subway, it will be a different issue. Okay, and for the time efficiency, right? We found that 80% of attacks takes less than 900 seconds to complete when act points are randomly chosen globally. Okay, we do not pre-assume the location of the user. Okay, but if you already know this user is, for example, in China or in a particular city, then you can narrow down this searching time. And we found that most of the time is spent on waiting for the network responses. Because when you refresh your location, right, basically you want to let the service provider know that your location is changing. So there's a waiting time, and that because you do a lot of wrong, right? So that costs a significant portion of the time. And this basically, these two figures basically shows that if you can guess the victim's location, say to a city or to a country, then you can save your time by avoiding random guessing on other locations. And here's the effectiveness of long-term tracking. The idea is that we know this Nature paper in year 2013 saying that if you can recover the top 4 locations of a particular user, then it can be linked to your real ID with a very high probability. But that experiment was conducted based on the cell tower IDs, right? So 4 different cell tower ID can be illegally linked to a particular user. So the recovering the real user ID, not just his user ID on the app, the real user ID is basically mapped to the problem of can you recover the top N locations of this particular user. So we follow the same approach. So obviously, if the ground truth has the top 3 locations as the red circles, if we can recover 2, that's basically 2 of 3. If we can recover all of them, that would be great. And in our case, our top N location is much more fine-grained. Okay, it's not a cell tower ID, right? If it's based on Wi-Fi, then it is much smaller area. So we just do this within our 3-week experiment period, right? And we find that for all three apps, we achieve high top 1 location coverage, and these top locations are much more fine-grained. And this is basically the table that summarizes the result. And now I want to show you a attack demo. So first of all, you see the target is in the blue circle, which is my lab at SUNY Buffalo. And then we first random guessing. Okay, so we use trilateration. So this red dot is a anchor point we set an arbitrary location, right? And we set 3 of them. This picture shows the closest one. And the arrow now shows in the bottom of the window says that this is 1898829. This is a huge error, right? That's by no means. And now we start from the trilateration, and then we try to narrow down the result of the location, and then we use space partition to further narrow down to improve our estimation. And the pictures on the right basically shows the stuff we running in the virtual machine, right? And this on the right bottom is the screen, right, of the so I assume this what happened? This should be, come on. Why? What happened? Apologize. Okay, so it's now actually wrong. So whenever you see 3 circles, they are trilateration, and why does it show on my screen? And each time we show the closest point in red.
Which app are you using right now for the tracing?
Well, which app, which social networking service you're exploiting right now for this tracing?
I think I believe this one is for Skype. So when you see a single circle, that's we use space partition to further narrow down the location. Yeah, and eventually it stops here. So in the end, because the accuracy also relies heavily on the available location information, because it's an indoor target. We don't have the GPS, so the best possible location information is through Wi-Fi. So this is just from the next building. So the arrow is now shows a little bit less than 40 meters. Okay, so in the interest of time, I will skip the defense mechanism, because there are so many different defense mechanisms try to obfuscate the location. And we did this only because when this paper was first submitted to CCS, they said that we do not accept pure attack paper. You have to propose some defense mechanisms. So then we have to add something. So basically, I'll skip this. So the concluding remarks. So we have developed automated attacks for the first time against the popular LBSNs with hundreds of millions of users. Proximity-based friend discovery poses serious threats to the user's location privacy. So automated user tracking attacks without hacking into LBSN service can be carried out without much technical difficulty or resources, and it can be scaled. And we already know some of the groups that try to deploy a lot of virtual machine instances and try to localize user. So and it is very important to protect the user's location privacy. as everybody agrees. So we believe that people should be able to take the control of their own personal location data. And maybe an open source personal location obfuscator controlled only by the user him or herself is desired. Okay, so the paper appears at SMOB Hawk 2014, and this is joint work between SUNY Buffalo and Shanghai Jiao Tong University. And thank you. Questions?
So if you only authorize this service to some friends, so would that eliminate the tag scenario? So in the authorized scenario.
Yeah, as we showed in the previous survey,
I think like Google Plus and Facebook.
Right.
so that depend on different apps, right? And I talked with conscious student last year, CCS. They did the tag on the Facebook,
Oh, okay.
so pretty much the same.
You don't need to be friend.
I don't know the details about the Facebook. Okay. So he said that later on he found that the Facebook has a new feature they can do. But in our case, in some cases, you don't have to be the friend, as I said in the here. For example, in the WeChat, right? You just show the people nearby, right? You don't have to be the friend. And in the Momo's case, you just search, the user's ID. Sometimes you need to know the user's ID, right? If we want to select a target to track, right? Or if we pick up a random user ID, and it may not be as meaningful, right? You track a random person, and what's the purpose of that?
So in your study, on average, how many tracing you did for each participant? How many times?
How many times? We performed that 3 weeks.
Right,
The
but
experiment.
Each time you start tracing, right, and then finish it. So you're not tracing it like every second or something, right? So
We record all the information and run the attack. So for the asynchronous attack is that during this, I have to say, during the 3 weeks of experiment, sometimes the server crashed. So
because I noticed you find out all the top 1 address in all applications, which I believe is probably their home address. That's my guess. So, but for the second address, didn't find out very many. I wonder, this maybe depends on how many points you have sampled.
Right.
So,
Right. I can't remember the exact details. Yes.
So you said like if the points are chosen globally, you are able to localize you are able to find the location in 900 seconds, right? In 80% of the cases, you are able to find the location in 900 seconds.
Right.
So, like on an average, if you know the city, how much time would the algorithm?
If you know the city. Okay. So
an average size city.
So you see, in this in this slides, the left picture is that you random guess. The right picture is that you know the city. So you can see, this the CDF of the tracking efficiency. It greatly improves, but the exact numbers you can find it in the paper.
Any other questions? No, that's it.
thanks.
Thank you.